Hey, how's it going? Hello? Oh, wait. Okay, I could not hear you. One second. Okay, I can hear you now. Can you guys hear me?
Yes, sir. Loud and clear.
All right, hello, Peter, Roseland, and Miguel. Good to see you guys here. How's everyone doing today?
Not too bad.
Not
A
too
little
bad.
early, but I'm good.
Okay, okay. It's a Friday. It's a little early in the morning as well, but Um, does anyone get a chance to look at the? Uh, yeah, Miguel is having some mic issues, but he'll probably come back. Does anyone have a got a chance to look at the implementations, trying out a few things?
So I unfortunately didn't have time, and I'm still kind of trying to understand soft actor critic generally, but I don't want to take away time from the people that actually did implement it. So maybe at the end I can ask some questions.
Yeah, that'll work as well. I think according to sort of the activities going on in the chat, it seems me and Roseland did the implementations. I don't know if anyone else did the implementations as well. Um, so Roseland, have you had any success with trying out different environments? Because I remember you said the mountain car continuous works.
It works, but it was about the spin up implementation, not mine,
Oh,
not
okay.
yet.
I see. You said this spinning up implementation works for the continuous mountain car, right?
Yes.
Yeah,
So their algorithm logic should probably be okay.
I see.
We can stick to it, and that's
Yeah,
actually what I'm trying to reproduce now. Just the
yeah.
PyTorch.
I'm trying that too. Unfortunately, it's not quite working. Perhaps I should share my screen. But before I do, so I see a couple more people joined. Sharon and Nicola. Did you guys also have a chance get a chance to try the implementation? Huh? Maybe it's a mic issue. Um. Okay. We can probably.
I could implement something with someone else's code, and I'm trying to use the CleanRL platform, but I'm having some trouble with it.
Okay. We can definitely talk about that. And remember, feel free if anytime you run into some trouble, um, since we're all implementing, feel free to post it in the monthly dev chat. Either myself or other people will be more than happy to help you. Okay. One thing I would like to do, first of all, is to maybe share my screen. I guess I'll be talking about my implementation and some of the things that frustrate me, and maybe we can take a look at how our implementation is different from how my implementation is different from the spinning up, because I think they're very close. So let me share my screen. Can you guys see my screen right now?
Yes, we can. Yep.
Okay. So what I'm gonna do is to open two um, websites. Okay. So I implemented the algorithm. Oops. Just kind of started from scratch. And then I compared this part of the code, the major part of the code, with the spinning up, um, and all the major part of the code looks very similar, but it's just not having the same performance. And I think it has something to do with the action squashing, which I already implemented, but it's also not quite working. Um,
Wait, so did you manage?
by the way, I think it's Sharon. I think your mic might have some issues. Just maybe something you can consider is you just quit. I was just thinking, if you have mic issues, you can always join the meeting by using your phone, and phones' mics are usually better. Um, okay. Um, so I guess one thing we could do is just sort of go over the algorithms again and see what we missed. So for the SAC, what I initially did was to initialize a policy. So some layers, and I output a mean and a standard deviation for for each of the actions in the action space. Um, and then in this case, when I do the forward, I pre-process the observation, and then get an action mean and the actions log standard deviation. And that's something that is sort of pointed out in the spinning up implementation, which is in a lot of other algorithms, when they implement the log standard deviation, it's state independent. However, in the SAC case, that would be state dependent. So that's something that I noticed right off the bat. So if you look at the SAC implementation talk, they have this, you should know, the way standard deviations are parameterized. So in other reinforcement learning algorithms, the log STD does with state independent parameter vectors. And what they do is to uh, instead of saying self dot log stdx, they'll just say is equal to log std of a bunch of zeros, so that the log standard deviation is independent from the action, from the state. So that's something that I noticed. And the other thing that I noticed for the spinning up implementation is how they sort of normalize the action standard deviation. If you go to their implementation and go to their core.file, they have this part. Um, um, well, forgot which part it is, but there's some sort of normalization with the action standard deviation. And then what you would do is you initialize a soft queue network and a soft queue value function. And then you also have the replay buffer. You initialize all of those. And then you start running the game. Um, and then when you do the optimization, first thing you would do is you calculate the soft value loss. So that would be the first value function here. Uh, in that case, one thing that I noted is the actions are sampled according to the current policy instead of the replay buffer. So that's something that is kind of interesting. So what they do is, you get the observation action rewards next observation and the duns from the experience replay. However, you resample the actions. And then you do everything from there by calculating the log probabilities and stuff like that. Um, and then eventually you calculate two soft Q values by using you two soft Q networks, and then you get the minimum soft Q values. And now, yeah, go ahead. Was someone gonna say something?
I'm not sure, but since it has come to this, I think in the spin-up implementation, they do not resample the actions each time. They just use the actions from the buffer.
Actually,
Right.
I think they do. But let's look into it. So if you look at the SAC, so in this case, it would be the value loss, right? And then so that will be here. And how do they
V
calculate?
or V loss.
Hmm. And how do they calculate the V backup is the minimum Q pi minus alpha times the log probability, right?
Mm-hmm.
And this mean Q pi, I think it's basically they're trying to resample it.
Ah, it's resampled. Indeed, I see.
So as you can
Okay.
see here, you have the pi, the Q1 pi. I think the Q1 pi is saying it's resampling, but let's take a further look, right? So what does it
Yes.
do?
Okay.
Yeah.
It takes in the observation plus the pipe, which is also like the output of the policy. So it's
Right.
resampled.
Exactly. It takes into the output of the current policy, which means it's doing the resampling. So that's this part. And since we use the torch.nogred, it means the minimum soft Q value would not have any gradient. And that's why when we do the forward pass on the value function and then do the loss function, um, it'll only have impact on the value loss instead of having any impact on on the on the on the policy. So that's how we calculate the value loss. And then when we calculate the soft Q value loss, what we do is we get the Q values from both of these networks with the gradient, and then we calculate the target, which is the rewards plus 1 minus duns times the discount factor gamma times the target the value function target network. So that would be this part right here. So the rewards corresponds to this part, and then the gamma corresponds to this part, and then the value function corresponds to that one. And notice they use this parameter, which means this is the target network instead of the actual the original value network, I guess. The only thing that is different is I have this one minus stance. Uh, that is very common when you're calculating the TD targets. And then what you would do is you minimize the loss between the first soft Q value and the soft TD target, and the second soft Q value to the TD target. And lastly, what you would do is you calculate the actor loss. So that would be this part. They're saying they're using this reparameterization trick, which is eventually mentioned at the appendix. So that's kind of a quirks of the paper. So what you would do is you generate the actions first, which is this U. So that will correspond to this part, and then you get the and then you normalize it by using the 10 function, or you using the action squashing to get the actual actions you're going to execute. So that's the resample action 10. And then when you calculate the log probability, it's also a little bit different. What you would do is you get the log probability of the original actions being sampled, and then you minus this torch.log 1 minus the 10 square u. Um, so um, right. So the 10u becomes the squashed actions, and then you take it as square. And then I noticed in a lot of implementation they add a minimum value when they calculate the log probability, which is just some very small scalar value like 1e minus 7, so that this thing doesn't necessarily approach to zero or something. I think it's just to help with the precision errors that sometimes happens. And then again, you calculate the minimum soft Q value, and then you minimize the loss by comparing the soft Q value. Sorry, you calculate the pi loss, which is right here. You get the minimum soft Q value, and then you get the alpha times the log probabilities minus the minimum soft Q value. So that's how you calculate the losses, and that's pretty much it. And in the end, you have this parameter, this part of the code, and that's how you update the target network. So that would be this part of the implementation. That would be this part right here. Yeah, so that's basically what I got so far, and it's not quite working. So when I compare the results, run it for 4 million time steps for the Hopper bullet inf, which should be a fairly easy environment, and it's not learning anything. It's a little bit frustrating, and I've checked multiple things. I think I'm still in this process and trying to figure out exactly what went wrong. Yeah. Do you guys notice anything that might be worth mentioning? Um, when calculating, yeah, go ahead. Go ahead.
I guess should be okay. No questions for now.
Okay. One thing that I noticed
With
with,
steps.
beg your pardon.
When are you doing your the gradient learning steps? Because I think the paper at the end says they did it like once every step or once every 1,000 steps, and that kind of changed things. It's at the very last page of the paper.
It's at the very last pages of the paper.
Yeah, that little blurb at the bottom. Yeah.
Like here?
Yep.
Oh, I see. I see. Training curves for additional baselines. Soft active critic with hard target value update differs from the standard. Oh, I see. I see. So, right. This is actually how I would have originally implementing it. Right. So the way they would do it is to, instead of doing this, what they would do is to instead just copy it directly. So they would use a function like this.
Okay.
So they would just use the value target load the current state from the value function every 1,000 time steps. So I think that would be just a different way. It's probably not going to impact the performance of agent significantly, as shown in this figure.
Right. Yeah. Okay.
Yeah, thanks for pointing out though. It is it is an interesting point I didn't quite realize. The other thing I want to sort of talk about is the sort of the reparameterization trick. In a lot of the implementation that I've seen, um, especially with PyTorch, they do this R samples thing instead of doing just the sample, which I can probably show you. So this would be, for example, a sort of a successful implementation. It's in here. I'll post it in the chat as well. And basically in here, when they do the sample, this is what they do. They get the mean and log standard deviation, and then they create the normal distribution. And then, so when looking at this, it's often helpful to look at the action squashing part of the paper. So if you look at here, the U here is essentially the XT. And notice how they do the R sample instead of the sample. And when you Google it, PyTorch R sample, And apparently the R sample would be a little bit different. So it's called something like a pathwise derivative. The other way to implement stochastic policy gradient would be use the reparameterization trick from the R sample method, which is something that I sort of have a hard time understanding of what exactly it is and should we use the method. Because yeah, I don't know exactly what it is. I saw some couple blog posts on the reparameterization tricks, but they're kind of confusing. I don't know. Does anyone have a good understanding of what the reparameterization trick is?
I would not say that I perfectly understand it, but the idea is that since we sample the actions from a normal distribution,
Mm-hmm.
when we do the back propagation, the gradient is always zero.
The what?
Because the gradient
Uh huh.
is always zero. So instead, they use the said reparameterization trick to make the gradient not zero. So the policy actually learned something. So I thought PyTorch automatically did the reparameterization trick as TensorFlow, but it seems that we should probably be using our sample. Otherwise, it's for now.
Right, right. And why would it be? Why would the gradient be zero if we don't use the reparameterization trick?
Something about the expectancy, when they take the expectancy, it cancels out.
Huh.
Again,
Okay.
I'm not really well versed on the trick,
Yeah, that's okay. I can
but
also further look into
that's
this.
the intuitive idea.
Okay, interesting. Yeah, and the other question is, when should you use the R sample, or does it matter? Because in a couple other implementation as well, I noticed they do things very differently. So, for example, in this very popular repo by Prince24, he basically uses R sample whenever he can, right? So
Yes,
that
yes.
yeah, so that's the sample for the Gaussian policy, which means whenever he generates an action, is always using the reparameterization trick. However, in a lot of well, in one other depot, I guess they're not using it always. Assuming if I can find it.
Mm, what is the framework used?
I don't remember. I was just looking things up randomly online, which I can't seem to find right now. But essentially, they use the resample only when it's with the agent. So in a lot of other cases, they don't really use it. Yeah, I can't find it right now. Sorry about that. Um, really? Yeah, unfortunately, I couldn't find any. And the R sample thing doesn't seem to be the case with the spinning up implementation as well. If you um, if you look at the spinning up implementation, they don't seem to exactly have that R sample thing. It just seems when the R sample is essentially this QPy, and essentially what that would happen is um, you would essentially run the pi again, which is pretty much running the whole policy and resample on a current distribution, and then you just pass it in. That's pretty much it. I don't really see how they're doing the reparameterization trick, I guess.
I think you should wait a second. The reparameterization is done in the core.py. If you check out line 69, if I'm not mistaken.
Oh, I see. I see.
So instead of doing like a normal mu STDs, they instead do mu times a random normal with the same shape as the mu times the STD. So that's the reparameterization right there.
Okay, I see. Okay, that makes sense. Because if you look at the PyTorch source code for the R sample, so if you go to the normal distribution and then you go to this R sample, you can actually see the difference between the R sample and sample. And in the R sample, what they would do is that they get this epsilon, which I would imagine will be similar to this part of the code, right?
Oh yes, that's it. Yes.
Yeah. Okay. So they're doing the reparameterization when they do the optimization.
It's also in the paper.
Yeah. 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 It's just kind of hard to understand that part because I don't know what they are. Why do they use it or things like that?
I see.
Um,
So maybe that's why the our policies are not learning anything.
I mean,
Our sample.
I mean,
Did you
I.
try running some experiment with that?
Hmm,
Not yet.
beg your pardon.
Did you try to run some experiment with the R sample instead?
Yes, I did, but maybe I was setting it up differently, and it just wasn't working quite well. So, for example, even if with the code that I just sort of showed, I have R sample somewhere, like for example, R sample here and R sample here, and it just wasn't working, and I don't know why. But perhaps one of these places it shouldn't be R sample or things like that. Um,
Okay. In
yeah,
the torch no grad part, it either is fine since the gradient is not backpropagated anyway. But when we update the policy itself, we should have the R sample.
I see. So maybe this should be sample and this should be R sample, right?
Well, the first resampled action can be should be anyone. I think there's no difference in this case.
Okay. Yeah,
But
that's a fair point.
only when we require the gradient update should we use R sample.
Right, right. Yeah, that could be an issue. Yeah, I don't know. I guess. Oh yeah, yeah, it's here. So remember in the policy class, I have this minimum logs std plus blah blah blah. Notice how they also have that. So that's sort of copy from the spinning up baselines. I was just trying to copy them to see how I can make things out of it. I guess. Yeah, it just doesn't quite work. But I did solve some bugs along the way. For example, initially the soft Q loss would just simply blow up, so it'll just go to infinity. And eventually, I think one thing that really helped was to do the resampling of actions. So that's something that I didn't notice. And as soon as it did the resampling of actions, the gradient didn't blow up. So
Hmm.
yeah, yeah, I don't know. I'll probably have to take a second look at the spinning up implementation and see what else is missing. But yeah. Okay, I'll also probably try to read this reparameterization trick thing. Seems to be a very helpful post by Nicola. Um, yeah, I'll definitely try to read this. Uh, Rosalind, do you have anything to share? Maybe things you want to talk about with respect to the implementation, some experience, or hello? He's probably out for the bathroom break or something. But other than that, I guess I wouldn't have too much to talk about. Just because the implementation has not been very successful. The other thing that I would consider is maybe instead of doing um, sort of a monthly development cycle, maybe we could do like a bi-monthly development cycle because this is taking a lot of my taking a lot of time to, and I wasn't expecting to spend this much time on it um, because I have other obligations like research assistant and classes and stuff. So it's kind of hard to do this at the same time. I'll also probably try to put a poll in the Slack channel as well, just to get people's opinions on this. Um, I see. But yeah, other than that, I don't have much to talk about.
Hey, you hear me?
Yeah,
Yep. And I just switched to my mobile phone, so
it's
uh,
perfect.
I wanted to just ask something regarding reparameterization.
Okay.
So I'm now looking at your implementation, line number 230. So I haven't implemented any action continuous reinforcement learning algorithm so far.
Mm-hmm.
So from this, what I see, you obtain from this PG forward,
Mm-hmm.
you obtain for every action some mean and some standard deviation. Is that
That's
so?
yeah, that's correct.
Yes, and you have for that some common part of neural network, and then they split. Now I'm looking at your class policy. So you have these two ReLU functions, FC1 and FC2.
Right, right, right. Two linear layers, yes.
Yes, and then later on they split. So FC mean has its own parameters, and log STD has its own parameters.
That's exactly right, yes.
Yes. So I'm not sure, but what I wanted to say is that maybe
Mm-hmm.
when we go back to line of 230,
Okay.
when you do this just normal, you sample from that distribution, but I'm not sure that Torch can backpropagate through these logics and STD.
So I guess a direct answer to that would be actually it can, because there's another file in the CleanRL repo that deals with the continuous action space. So if you want to give it a try, just to play with it, there's this A2C continuous action. And then if you look at how it's being implemented, it's also probability normal distribution action equals probability dot sample, and then eventually the policy loss is the advantages times a negative log probabilities. And notice when we calculate the log probability is to use the actions that has been sampled from the normal distribution. So I would imagine the gradient would definitely work with this.
Okay, but
Uh-huh.
I cannot see clearly because I'm on phone and it is too small. In that
Oh,
other
sorry.
implementation, do you also have this resampled action Yermako equals probs dot sample or not?
It's not resample. In the other repo, it's just sample. But let me just send that part of the code to you. I'll post that also in the chat.
Okay, let me just switch. It is A to C continuous
Yes. Also, I just
in experiments folder or
just in the cleaner out folder because it's stable enough to put it there.
okay, okay, I see. And which line?
So that would be around line 140 to 144.
Yes, I see. Yes, I
Hmm.
see. Uh, so I don't know. Okay, but maybe it has to do something with this next line. Action equals props dot sample.
Hmm.
So maybe that way you tell PyTorch that it should backpropagate, but I'm not quite sure because I don't know PyTorch.
So usually, as long as you use the neural networks to calculate something, there's always gradient. So
Yes,
in
okay.
this case, you have the you calculate the logits and the STD, and then you calculate a normal distribution. Since this actions is calculated by using the neural network, therefore it has gradient. So
Okay, okay.
so I think that's the rough idea about the gradient in PyTorch. And then if you don't want to use a gradient, you can either say action dot detach, or just say with torch dot no underscore grad context manager, and then action dot probability dot sample. So that would look something more like the lines you were previously mentioning with the SAC file. So it'll look like
Yes, yes, I
probably.
see. But I tried to Google it, and I think uh, I found something that doesn't agree with your arguments. So I'll try to find it again, and then I'll share it.
Okay, yeah,
Maybe
absolutely. It
maybe
definitely
we
could be
didn't
wrong.
understand each other.
Hmm? Beg your pardon?
Maybe we didn't understand each other now. So
Yeah, yeah, probably. Um, the other thing that I would encourage you to look at is in the distribution, they actually gave you a reinforcement learning example for this. So if you just look at the, I'll also post this in the chat as well. So basically, when you look at the score function, so that's on the very top of the page, they tell you how to calculate the negative log probabilities for the essentially for the policy gradients, right? You create a categorical distribution and then you sample from that distribution, and then you create your loss by using the distribution.log probability action. And that's sort of the pattern that the cleaner out repository has been following for calculating the log probabilities. So, um, yeah. Rosalind, do you have any other further comments by any chance?
should be fine. But I had a doubt regarding the entropy. I guess it's not really used in this case, right?
The one now?
The entropy of the policy itself, not the log p pi, but the entropy.
Um, well, the entropy is using the soft Q values, right? What do you mean?
In the soft Q value, okay, it's the entropy of the policy for an action given the sample state, but the general entropy of the policy.
So when you see here, um, when you see this part of the code um, where the let me see.
Yes, this one. HP. Wait.
So I remember my impression was that the Q value would definitely have part of the entropy in it. So, for example, this would be the definition of an entropy, right? The expectation of random variable sample from the distribution, the negative log probability of that distribution. So, and if you look at a Q value, this is the Q value, right? The Q value minus the alpha times the log probability. So, and this is also the value function as well. So it's essentially saying the Q value, the original value function, plus the entropy of the probability distribution, right? Does that make sense?
Yes, that's right. Yeah, yeah, sure.
Right, right. So I think,
My question is actually regarding the not the entropy used to compute the Q backup, but instead no. In this case, it's B backup. Instead, it's the entropy they usually log into the tensor board to
oh,
see
right, right,
whether
right,
the
right, right. Yeah, that's not related. I was just trying to get a feeling of if the policy is converging to some local minimum really quickly. Like for example, if the entropy just goes down straight or goes down bottom, I know something would have gone wrong.
Okay, so the idea is okay, not the idea, but let's say we have a batch of 100 states, right? And we
Hmm.
compute the entropy of the action
Hmm.
over all these states. Do we want the mean of this entropy or the sum of
So
those
for
functions?
the entropy, I'm trying to think. Because I know for so right for the entropy, I think you would use mean because you get the 100 samples and then you're trying to get the mean entropy,
Yes, I
right?
see.
Um, so if you
Fine,
calculate the
fine.
log probabilities, for example, let's say you have three actions, your action space has three values, three scalar values, and when you calculate the
Yep.
entropy, it's basically going to be have you'll have a shape of 100. So for each of those samples, you would have an entropy, but for the log probabilities, you would have a shape of 103. The other three is a log probabilities for each of those scalar values. And it's generally acceptable for you to add those log probabilities up. Right.
Okay, should be no problem.
Yeah. So that would look something like this. Let me see. So if you just look at the log probability of the sampled action, it's going to look something like this. Do you kind of see? So and then it's
Yeah, I can
generally
see.
acceptable to sum it up so that you have like your batch shaped log probabilities. So you just add them up. So for the log probability is generally acceptable. For the entropy, um, you usually just keep it. I think. Let me think. It's also here. Oh, sorry. For the entropy, it's probably the same as well. So you probably would have to sum it up. Okay. Really? Wait, why would there only be three?
I think it's summed over all the states, probably.
Oh, you know what? I also just noticed something. Is this gonna be an issue? Let me see. So if I get that, and now the probability should have 32. And now if I do the entropy, it should have 32, which is the batch size. And then, right, what you want to do to sum it out by the first dimension. Right. Speaking of which, that's a very uniform entropy, which is probably not a very good thing. But yeah, so that's sort of my take on it. Right. Let me see.
I still need to update my implementation with the R sample.
Right. So for example, if you look at the mean and the standard deviation, so this is a logis for the mean, and this is the standard deviations, right? So essentially, this would correspond to this, and when you sample from it, there's going to be a negative log probability associated with this and also one for this and this, and for this and this. That's why you need to sum the entropy and the log probability up. So apparently there's this assumption that log probability and entropy are additive, so you can just add them up. I read it somewhere. I couldn't give you a reference for now, but that seems to be the general way people have dealt it.
You can add them up.
Yes.
Oh, okay, okay. I see. Yes, indeed.
Hmm. So, excuse me. Okay. So I think the next step would be, for us to keep working on this. I personally will check out more about the reparameterization trick and see how to use it correctly. And so we probably would spend more than a month for the SAC, both because of the current difficulties that we face, but also because of the upcoming holiday season. So I mean, if it's holiday, we don't have to meet. Um, but yeah, um, any further questions or comments by anyone?
Well, I think the R sample just solves my implementation. I have a steady decrease in the policy loss.
Oh, really? Wait, shouldn't shouldn't the policy loss go down?
Yeah, it wasn't going down that smoothly before.
I see, I see. How about the episode rewards? Is it going up?
Uh, it's still at zero. Actually, I'm still testing on Mountain Car,
Okay.
continuous.
So
And
one.
according to soft, I copied exactly the hyperparameters of the spin-up implementation, and
Uh-huh.
their algorithm solves it after 20 epochs. But before the 20 epochs, it's also stagnating at zero
Okay. Well,
for the
20
period.
epoch should be something really fast, right? Should be because it's 20 episodes, and each episode that would be like um maybe 40,000 k steps, maybe 40,000 steps.
20 epochs would be 80,000 steps, like 80 or 100,000.
Okay, so it definitely takes some time, but not too long.
One thing you might want to check is that I think it should be all right. You do the updates after each transition, right? Let me check again.
Yeah, so that would be every step.
Every step allows in the paper.
Hmm.
In the spin up, I don't know if you noticed, but they do it at the end of each episode.
Really? Let me check it up. Check it out. I think they do it every steps. Actually, you're talking about this part, right?
Yes, because it's in the if done or max episode length reached.
Oh, yeah, that's a good point. That's a good point.
But the difference is quite subtle. I think there's not much influence because if you do it one step at a time, you're basically how to say that intuitively. You just sampled one transition, so what's the probability it's gonna be used during the next update? It's quite low. But if you wait until the end of the episode to do the update, I think there is more, I don't know, variety in the novelty in the sample transition, so the policy can actually
Hmm.
learn
Right. So,
something significant knowledge.
mhm. But I also think that will be a common pattern of the DQN as well. And the way the DQN
Yeah.
handles the replay memory is they still do this experience replay and learn at every time step. But what they do is they set a certain number of time steps before they resample from the before they sample from the experience replay. So in this case, it will look something
Yes.
like this. If the length of the storage is greater than 2000, which means I have to run 2000 time steps before I do any learning,
At
right?
least.
Right. So I think that'll help with the problem. So it's not like only run for one step and then just trying to learn 33 steps. Uh, yeah, it's not
Yes,
like
but
that.
this is a. I think there is a tricky point here. If they wait until the buffer is filled up a little bit, it's probably to just make sure you have enough samples to actually sample.
Right. And the reason for that is, yeah, to so that you have more experience. But then you sample it at every time step is to apparently to deal with the catastrophic forgetting problem, so that you keep trying to relearning the past experience.
Okay,
But
I
I could
guess
definitely,
that
I,
makes
I
sense.
could definitely try this out too, just to see how that would go at the end of the episode. Try optimize it that way. Um, yeah, I don't know. I'll have to see. All right, so I think this will be pretty much it for the day. Thank you everyone for coming.
Can I ask you just if you could list some easy environment to solve, easy environments to solve, so that I can test my implementation when it's done? Because
Uh huh.
I haven't tried any action continuous agent so far.
Yeah. So in general, with the continuous case, it's very difficult. You always have to wait for a very long time before any simple problem can be solved. So, oh, what is happening here? So one thing I would recommend is, okay, let me go to here. Go to cleanrl.costa.sh, and then over here you can find my benchmark on a variety of environments, and
Okay.
and then especially in the bottom where you can see all of these inverted pendulum, these continuous action spaces, so you can just kind of see which ones converge faster. So a couple things that I noticed converge pretty fast is, for example, the hopper environment. um, it goes from 15 to 200 just within 50K time steps. So I think it'll be very easy for you to tell whether the initial algorithms works, whether you can learn even the simplest thing.
Okay. Thank you.
Yeah, not a problem.
Hopper.
Yeah, all of them run for pretty much 2 million time steps. So probably you need some you need to check those out to figure out exactly which one is more suitable for you.
Okay. Thank you.
Yeah, no problem. My pleasure. Um, okay. Does anyone have any last comments? Okay. I want to thank everyone for coming. Um, So after this, I'll upload the video to YouTube so that people who missed it will have a chance to see. And for those of you who haven't had the chance to try it out, feel free to you can even just use my implementation so far as a base. Try to see if you understand most of the implementation, and we can work from there. Or if you want, you could implement from scratch. Both are very valid approaches. Let me know if you have any troubles with the cleaner out, the project setups, and everything. And I will have a good weekend, and I'll see you next time then.
Would you mind if I shot you some questions on Slack later?
Yeah, of course. Yeah.
Okay, cool.
Thank you. I'll see you guys later. All right. Bye bye.